Well, you know, sometimes the most important thing comes in the smallest packages. And I'm going to try to convince you in the 15 minutes I have that microbes have a lot to say about questions such as, are we alone? You know, and they can tell us more about not only life in our solar system, but also maybe beyond. And this is why I am tracking them down in the most impossible places on Earth, in extreme environment where conditions are really pushing them to the brink of survival. Actually, sometimes me too, when I'm trying to follow them too close. But here's the thing. We are the only advanced civilization in the solar system. But that doesn't mean that there is no microbial life nearby. In fact, the planets and moons you see here could host life, all of them, and we know that. And it's a strong possibility. And if we were going to find life on those moons and planets, then we would answer questions such as, are we alone in the solar system? Where are we coming from? Do we have family in the neighborhood? Is there life beyond our solar system? And we can ask all those questions because there has been a revolution in our understanding of what a habitable planet is. And today, a habitable planet is a planet that has a zone where water can stay stable. But to me, this is a horizontal definition of habitability because it involves a distance to a star, but there is another dimension to habitability, and this is a vertical dimension. Think of it as, you know, conditions in the subsurface of a planet where you are very far away from the sun, but you still have water, energy, nutrients, which for some of them means food, and a protection. And when you look at the Earth, very far away from any sunlight, deep in the ocean, you have life thriving, and it uses only chemistry for life processes. So, when you think of it, at that point, all worlds collapse. You have no limitation, basically. And if you have been looking at the headlines lately, then you would see that, you know, we have discovered a subsurface ocean on Europa, on Ganymede, on Enceladus, on Titan. And now we're finding geyser and hot spring on Enceladus. Our solar system is turning into a giant spa. For anybody who has gone to a spa knows how much microbes like that, right? So at that point, think also about Mars. There is no life possible at the surface of Mars today, but it might still be hiding underground. So, we have been making progress in our understanding of habitability, but we also have been making progress in our understanding of what the signature of life are on Earth. And you can have what we call organic molecules, and these are the bricks of life. And you can have fossils, and you can have minerals, biominerals, which is due to the reaction between bacteria and rocks. And of course, you can have gases in the atmosphere. And when you look at those tiny green algae on the right of the slide here, they are the direct descendant of those who have been pumping oxygen billion years ago in the atmosphere of the Earth. When they did that, they poisoned 90% of the life at the surface of the Earth. But they are the reason why you are breathing this air today. But as much as our understanding grows of all of these things, there is one question we still cannot answer, and this is where are we coming from? And you know, it's getting worse because we won't be able to find a physical evidence of where we are coming from on this planet. And the reason being is that anything that is older than 4 billion years is gone. Our record is gone, erased by plate tectonics and erosion. This is what I call the Earth's biological horizon. Beyond this horizon, we don't know where we are coming from. So is everything lost? Well, maybe not. And we might be able to find evidence of our own origin in the most unlikely place, and this place is Mars. How is this possible? Well, clearly, you know, at the beginning of the solar system, Mars and the Earth were bombarded by giant asteroids and comets. And there were ejecta from this impact all over the place. And Mars kept throwing rocks at each other for a very long time. Pieces of rocks landed on the Earth, pieces of the Earth landed on Mars. So clearly, those two planets may have been seeded by the same material. So yeah, maybe Granddaddy is sitting there at the surface and waiting for us. All right? But that also means that we can go to Mars and try to find traces of our own origin. Mars may hold that secret for us. This is why Mars is so special to us. But for that to happen, Mars needed to be habitable at the time when conditions were right. So, was Mars habitable? We have a number of missions telling us exactly the same thing today. At the time when life appeared on the Earth, Mars did have an ocean, it had volcanoes, it had lakes, and it had deltas like the beautiful picture you see here. This picture was sent by the Curiosity rover only a few weeks ago. It shows the remnants of a delta. And this picture tells us something. Water was abundant and stayed pounding at the surface for a very long time. This is good news for life. Life chemistry takes a long time to actually happen. So this is extremely good news. But does that mean that if we go there, life will be easy to find on Mars? Not necessarily. Here's what happened. At the time when life exploded at the surface of the Earth, then everything went south for Mars, literally. The atmosphere was stripped away by solar winds, Mars lost its magnetosphere, and then cosmic rays and UV bombarded the surface, and water escaped to space and went underground. So if we want to be able to understand, if we will be able to find those traces or those signatures of life at the surface of Mars, if they are there, we need to understand what was the impact of each of these events on the preservation of its record. Only then we will be able to know where those signatures are hiding, and only then we will be able to send our rover to the right places where we can sample those rocks that may be telling us something really important about who we are. Or if not, maybe telling us that somewhere independently, life has appeared on another planet. So to do that, it's easy. You only need to go back 3.5 billion years ago in the past of a planet. We just need a time machine. Easy, right? Well, actually, it is. Look around you. That's planet Earth. This is our time machine. Geologists are using it to go back in the past of our own planet. I'm using it a little bit differently. I use planet Earth to go in very extreme environment where conditions were similar to those of Mars at the time when the climate changed. And there I'm trying to understand what happened. You know, what are the signatures left? What is left? How are we going to find it? So for one moment now, I'm going to take you with me on a trip into that time machine. And now, what you see here, we are at 4,500 meters in the Andes. But in fact, we are less than 1 billion years after the Earth and Mars formed. The Earth and Mars will have looked pretty much exactly like that. Volcanoes everywhere, evaporating lakes everywhere, minerals, hot springs. And then you see those mounds on the shore of those lakes. They are built by the descendant of the first organism that gave us the first fossil on Earth. But if we want to understand what's going on, we need to go a little further. And the other thing about those sites is that exactly like on Mars 3.5 billion years ago, climate is changing very fast and water and ice are disappearing. But we need to go back to that time when everything changed on Mars. And to do that, we need to go higher. Why is that? Because when you go higher, the atmosphere is getting thinner, it's getting more unstable, temperatures are getting cooler, and you have a lot more UV radiation. Basically, you are getting to those conditions on Mars when everything changed. So, I was not promising anything about the leisurely trip on the time machine. You are not going to be sitting in that time machine. You have to haul 1,000 pounds of equipment to the summit of this 20,000-foot volcano in the Andes here. That's about 6,000 meters. And you also have to sleep on 42-degree slope and really hope that there won't be any earthquake that night. But when we get to the summit, we actually find the lake we came for. At this altitude, this lake is experiencing exactly the same condition as those on Mars 3.5 billion years ago. And now we have to change our voyage into an inner voyage inside that lake. And to do that, we have to remove our mounting gears and actually don suits and go for it. But at the time we enter that lake, at the very moment we enter that lake, we are stepping back 3.5 billion years in the past of another planet. And then we are going to get the answer we came for. Life is everywhere. Absolutely everywhere. Everything you see in this picture is a living organism. Maybe not so the diver, but everything else. Okay? But this picture is very deceiving. Life is abundant in those lakes. But like in many places on Earth right now, and due to climate change, there is a huge loss in biodiversity. In the samples that we took back home, 36% of the bacteria in those lakes were composed of 3 species. And those 3 species are the ones that have survived so far. Here's another lake, right next to the first one. The red color you see here is not due to minerals. It's actually due to the presence of a tiny algae. In this region, the UV radiation is really nasty. Anywhere on Earth, 11 is considered to be extreme. During UV storm there, the UV index reaches 43. SPF 30 is not going to do anything to you over there. And the water is so transparent in those lakes that the algae have nowhere to hide, really. And so they are developing their own sunscreen, and this is the red color you see. But they can adapt only so far. And then when all the water is gone from the surface, microbes have only one solution left. They go underground. And those microbes, the rocks you see in that slide here, well, they are actually living inside rocks. And they are using the protection of the translucent of the rock to get the good part of the UV and discard the part that could actually damage their DNA. And this is why we're taking our rover to train them to search for life on Mars in this area, because if there was life on Mars 3.5 billion years ago, it had to use the same strategy to actually protect itself. Now, it is pretty obvious that going to extreme environment is helping us very much for the exploration of Mars and to prepare missions. So far, it has helped us to understand the geology of Mars. It has helped us to understand the past climate of Mars and its evolution, but also its habitability potential. Our most recent rover on Mars has discovered traces of organics. Well, yeah, there are organics at the surface of Mars. And it also discovered traces of methane. And we don't know yet if the methane in question is really from geology or biology. Regardless, what we know is that because of the discovery, the hypothesis that there is still life present on Mars today remains a viable one. So by now, I think I convinced you that Mars is very special to us. But it would be a mistake to think that Mars is the only place in the solar system that is interesting to find potential microbial life. And the reason is because Mars and the Earth could have a common root to their tree of life. But when you go beyond Mars, it's not that easy. Celestial mechanics is not making it so easy for an exchange of material between planets. And so if we were to discover life in those planets, it would be different from us. It would be a different type of life. But in the end, it might be just us. It might be us and Mars. Or it can be many trees of life in the solar system. I don't know the answer yet, but I can tell you something. No matter what the result is, no matter what that magic number is, it is going to give us a standard by which we are going to be able to measure the life potential, abundance, and diversity beyond our own solar system. And this can be achieved by our generation. This can be our legacy, but only if we dare to explore. Now, finally, if somebody tells you that looking for alien microbes is not cool because you cannot have a philosophical conversation with them, let me show you why now and how you can tell them wrong. Well, organic material is going to tell you about environment, about complexity, and about diversity. DNA, or any information carrier, is going to tell you about adaptation, about evolution, about survival, about planetary changes, and about the transfer of information. All together, they are telling us what started as a microbial pathways and why what started as a microbial pathway sometimes end up as a civilization or sometimes end up as a dead end. Look at the solar system. And look at the Earth. On Earth, there are many intelligent species, but only one has achieved technology. Right here, in the journey of our own solar system, there is a very, very powerful message that says, you know, here is how we should look for alien life, small and big. So yeah, microbes are talking, and we are listening, and they are taking us one planet at a time and one moon at a time toward the big brothers out there. And they are telling us about diversity, they are taking us about abundance of life, and they are taking us how this life has survived that far to reach civilization, intelligence, technology, and indeed, philosophy. Thank you.